Hello and welcome to Petroleum Bites. Today we'll explore one of the most important artificial lift method in oil industry, the Electrical Submersible Pump (ESP). In this lesson we'll begin by developing a broad understanding of artificial lift methods and the well conditions that require their installation. We will then take an in-depth look at the ESP system, examining its lifting mechanism and how it builds pressure through multiple pump stages to efficiently move fluids to the surface. Following that, we will break down the key components of the ESP and go through the essential steps involved in designing an ESP system tailored to well and production requirements. Finally, we will conclude by discussing the main application, advantages, and limitation of ESP, providing a comprehensive view of their role in oil field operations. So, let's get started. Why are artificial lift methods generally used? In early stages of well production cycle, some oil wells are able to flow naturally due to high reservoir pressure. This pressure is sufficient to overcome drawdown, fluid hydrostatic pressure, and tubing friction, allowing hydrocarbon to reach surface at a certain wellhead pressure, as we previously discussed in IPR and VLP performance lesson. This natural flow depends entirely on the reservoir energy. However, over time the reservoir pressure gradually declines, and the well loses its ability to produce naturally. To maintain production, an artificial lift method is installed to create the necessary drawdown, enabling reservoir fluid to flow into the wellbore. The artificial lift system provides the additional energy needed for the produced fluid to overcome tubing friction and reach the surface at the required wellhead pressure. There are various artificial lift methods, each suited for different well conditions and applications. In this lesson, we will focus specifically on electrical submersible pump and explore its operation, design, and application in details. The electrical submersible pump is a type of multi-stage centrifugal pump designed to lift fluids by converting rotational energy into pressure and flow. The operating principle of centrifugal pump revolves around the conversion of mechanical energy into kinetic energy, which is then transformed into pressure energy to drive fluid movement. At the core of this process is the rotating impeller, which generates centrifugal force, drawing fluid into the pump and accelerating it outward. As the fluid passes through the diffuser, its velocity decreases and the kinetic energy converted into pressure. This process occurs across multiple stages, with each stage consisting of an impeller and diffuser pair. This gradual progression of pressure increase ensures the fluid reaches to the required discharge pressure for efficient lift to the surface. The ESP system is made up of several key components, each serving a vital function in ensuring efficient and reliable operation. At the lowest point of the assembly is the ESP motor, which provides the rotational force needed to drive the pump. Extended from the surface down to the motor is the ESP power cable, responsible for delivering high voltage electrical power to the system. This cable is designed to withstand harsh wellbore conditions, including high pressure, temperature, and exposure to corrosive fluid. Directly connected to the motor is the protector, also known as the seal section. The protector acts as a barrier, preventing well fluid from entering to the motor, while also equalizing internal and external pressure and accommodating motor oil expansion during the temperature changes. Positioned above the protector is the pump intake, the entry point of well fluid into the ESP system. Finally, the ESP pump itself, consisting of multiple stages of impeller and diffusers, enabling the fluid to be lifted progressively to the surface. The ESP motor serves as the powerhouse of ESP system, responsible for driving the pump and delivering the rotational movement required to turn the shaft and impellers. This continuous rotation is essential for maintaining steady fluid lifting from the wellbore to the surface. The motor's operation is based on the interaction between the two primary components, the rotor and the stator, through the principle of electromagnetic induction. The three-phase alternating current supply to the stator, generating a rotating magnetic field, inducing motion in the rotor and producing the necessary mechanical energy to drive the pump. The three-phase induction motor is the most widely used type of ESP motor, valued for its reliability, simplicity, and cost-effectiveness. However, for enhanced efficiency and performance, the permanent magnet motor, known as PMM, offers an advanced alternative. Unlike traditional induction motors, the PMM uses a permanent magnets mounted on the rotor to create a consistent magnetic field, eliminating rotor current losses and delivering high efficiency, greater torque, and reduced power consumption. Both motor types play a crucial role in ESP operation, with the choice depending on the well conditions, energy efficiency goals, and operational requirements. The ESP protector, also known as the seal section, is positioned between the ESP motor and the pump intake. It serves several essential functions. The primary role is to transfer rotational force from the motor to the pump through the thrust bearings, which helps manage the axial loads generated during operation. As the ESP motor runs, it produces heat, causing the dielectric inside the motor to expand. The protector compensates for this expansion, preventing excessive pressure buildup that could damage motor components. Additionally, it acts as a protective seal, preventing well fluid from entering to the motor, which could lead to dielectric failure, corrosion, and bearing damage. There are two main types of ESP protectors, each designed to handle specific downhole conditions. Labyrinth protector uses a series of chambers and baffles to gradually equalize pressure between the motor and the wellbore. Bag-type protector equipped with elastomer bags that expand and contract in response to motor oil expansion. The ESP cable is a specialized three-phase power cable that supplies the electricity from the surface to the ESP motor. This cable is engineered to withstand extreme downhole conditions, including high temperature, elevated pressure, corrosive fluid, and mechanical stresses. There are two primary types of ESP cables, chosen based on well configuration and operational needs. The round cable features a cylindrical cross-section, providing superior mechanical strength and flexibility. Flat cable has a flat cross-section with conductors arranged side by side, often used in limited space constraints. The ESP pump intake is the entry point where well fluids enter the pump before being lifted to the surface. The intake plays a critical role in regulating fluid entry and managing gas interference. There are two primary types of pump intake, each suited for different well conditions. Standard intake, a simple open design that allows fluid to flow directly into the pump without any gas or solid separation. It's used in clean well with low gas to liquid ratios. Gas separation intake, equipped with centrifugal separation technology. This intake removes free gas from the fluid stream before it enters the pump, preventing gas locking and maintaining stable pump performance in high gas-liquid ratio wells. The ESP pump stages are responsible for lifting well fluid from the intake to the discharge point at the surface. Pump stages are made up of multiple impeller diffuser pairs stacked in series to gradually increase fluid pressure and push the fluid upward through the pump. Based on flow direction and pressure characteristics, ESP pumps are classified into radial flow pump. In this design, the impellers push fluid outwards at a 90-degree angle from the shaft, generating high pressure but handling lower flow rates. Mixed flow pump. Here the impellers push fluid both radially and axially, creating a balance between pressure and flow. ESP pump stages can also be categorized based on impeller attachment and movement to floating stages, where impellers are not rigidly fixed but can move slightly along the shaft, reducing the mechanical wear and managing free gas more efficiently. Compression stages. The impellers are fixed securely to the shaft, offering a greater durability and efficiency in a stable flow condition with minimal gas or solid interference. The ESP pump curve is a graphical representation of the pump's performance across various operating conditions, providing critical insights into the relationship between flow rate, head generation, power requirements, and pump efficiency. It serves as an essential tool for engineers, helping them select the right pump and optimize performance based on well conditions and production goals. Every ESP pump has a recommended operating range, where to achieve the maximum efficiency and stable operation. The best efficiency point represents the optimal balance of flow rate, pressure, and energy consumption, ensuring minimal mechanical stress and prolonged equipment life. When the pump operates below the recommended flow range, it enters the downthrust condition. In this scenario, excessive downward force is exerted on the thrust bearing, leading to increased wear and potential bearing failure. Conversely, operating above the recommended flow range results in the upthrust condition, where fluid dynamics cause the impellers to lift away from the diffuser, creating instability and mechanical stress. This can lead to the bearing damage, misalignment, and accelerated wear on pump components. Both upthrust and downthrust conditions pose serious risks to ESP reliability, potentially causing premature failure of the pump and motor system. Therefore, maintaining operating as close as possible to the best efficiency point is crucial for ensuring efficient, stable, and long-lasting ESP performance. Designing an ESP involves a systematic and detailed process that considers well conditions, production requirements, and equipment limitations, balancing these factors to deliver reliable and cost-effective artificial lift. The first step in ESP design is to determine the required production rate, which is obtained from the reservoir's IPR. The IPR curve illustrates the maximum well deliverability and the absolute open flow, providing essential insight into the well fluid production potential, as we previously discussed in the IPR and VLB video. Next, we calculate the total dynamic head, TDH, the total pressure the ESP must overcome to lift fluid from the wellbore to surface. TDH is the sum of three key pressure components: elevation head, which is the vertical distance the fluid must be lifted; friction head loss, it is the pressure drop caused by the fluid friction in the tubing and flow restrictions; wellhead pressure, which is the required surface pressure to maintain production and facilitate downstream operations. Once the TDH and production rate are defined, the appropriate pump type is selected based on its ability to deliver the required flow rate and pressure. Referring to the ESP performance curve, we obtain the head per stage, which is used to calculate the number of stages needed to achieve the TDH. We also determine the horsepower per stage, essential for sizing the motor. Motor selection depends on the horsepower requirement. Each motor has a specific amperage and voltage rating necessary for proper operation, which in turn leads to cable and surface transformer selection. The ESP power cable size is selected to provide the required current amp to the motor while minimizing voltage drop over the entire cable length. Best practice of ESP design recommend that voltage drop shouldn't exceed 30 volts per 1000 feet of cable length. Once the cable size is chosen and total voltage drop is calculated, we can determine the required surface voltage and specify the appropriate surface transformer for power supply. Beyond these core steps, other critical factors and considerations influence the ESP design, including high gas-to-liquid ratio that require gas separator or gas handler to prevent gas locking, scaling tendency and formation of scale deposits at the pump's operating pressure and temperature, which may recommend using a mixed flow pump or installing a capillary tube for surface chemical injection. The presence of sour gases and high water cut, which demand using corrosion-resistant material to protect pump components. Also, sand or solid production can lead to having extra measures to protect pump parts against erosion and wear. ESP offer numerous advantages, making them an optimal choice for a wide range of well applications. They are practically well suited for high production rate wells capable of handling large fluid volume efficiently. One of ESP key strengths is its flexibility to operate in highly deviated and horizontal wells, where other artificial lift methods may struggle. It also has a limited capability of scale handling, especially when mixed flow pump is used or with applying proper chemical treatment. ESP also provide exceptional efficiency, achieving up to 75% efficiency, which is higher than many other artificial lift methods. Moreover, ESP require minimum surface infrastructure, making them an ideal solution for offshore platform where space is limited and surface equipment must remain compact. Despite their many advantages, ESP also have limitations that must be carefully considered during systems design and operation. High gas-to-liquid ratio pose a significant challenge as excessive free gas can lead to gas locking or a sharp decline in pump efficiency. Abrasive wear from produced sand also threaten ESP reliability, causing premature damage to critical components like impellers, diffusers, and bearings. When ESP require maintenance or replacement, retrieval and reinstallation necessitates a workover rig, which can be costly and time-consuming operation, practically in offshore environments. Additionally, ESP are best suited for medium to high production rate and may underperform in low production wells, where insufficient flow can lead to overheating, inefficient operation, and equipment failure. In conclusion, ESP remain one of the most efficient and widely used artificial lift method for high production oil and water wells. Their high efficiency, space-saving design, and adaptability to various well conditions make them an excellent choice for high-rate production operations. However, they require careful design, continuous monitoring, and proactive maintenance to mitigate their limitation and to ensure long-term reliability. That brings us to the end of today's lesson. I hope you found this video informative and valuable. If you have any questions, feedback, or suggestions for future topics, please feel free to share them in the comments section below. You can also reach me directly via email at petroleumbytes@gmail.com. I'd love to hear your thoughts and ideas. Thank you for watching, and I look forward to seeing you next time.